Good day everyone, my name is John Oliver Busidad and I am going to discuss the tree of data structure. So without further ado, let's start. A tree is an infinite non-empty set of elements. In the context of data structures, a tree is a collection of elements organized in a hierarchical structure. The term finite non-empty set indicates that there is a limited number of elements and the set is not devoid of content. It is an abstract model of hierarchical structure. The term abstract model implies that a tree is a conceptual representation used to understand and describe hierarchical relationships. It is not a physical tree but a way of visualizing relationships in a structured manner. Consists of nodes with a parent-child relation. In a tree structure, elements are represented as nodes. Each node has a parent-child relationship with other nodes. The parent node is the one higher in the hierarchy, and the child node is the one lower. This hierarchical arrangement helps organize and represent relationships efficiently. Applications: Organization charts. Trees are used to model organizational structures where each node represents a position or role within an organization. The parent-child relationships illustrate the hierarchy of positions or roles. File systems. Trees are employed to organize files and directories in computer file systems. Directories are represented as nodes, and the parent-child relationships show the hierarchy of folders and files. Programming environments. Trees are utilized in programming environments to represent the hierarchical structure of code. Abstract syntax trees and parse trees help analyze and understand the syntax and structure of programming languages. Introduction to tree. Nature view of the tree. Computer scientist view. Tree terminology. Root. Node without a parent. The root of a tree is the topmost node, denoted as A in this case. It is a node that does not have a parent, and it serves as the starting point of the hierarchical structure. Siblings. Nodes share the same parent. Nodes that share the same parent are called siblings. For example, in the tree structure, nodes B and C are siblings as they have the parent, or the A. Internal node. Node with at least one child, A, B, C, and F. An internal node is a node that has at least one child. Nodes A, B, C, and F are internal nodes in this context. External node or leaf. Node without children. E, I, J, K, G, H, and D. An external node or leaf is a node without any children. Nodes E, I, J, K, G, F, and Z are examples of external nodes in the tree. Ancestor of a node. Parent, grandparent, and grand-grandparent. The ancestors of the node or the nodes that lie on the path from the node to the root. This includes the parent, grandparent, and so on. Descendant of a node. Child, grandchild, grand-grandchild. The descendants of a node are the nodes that lie below in the hierarchy, including children, grandchildren, and so forth. Depth of a node. Number of ancestors. The depth of a node is the number of ancestors it has. It is a measure of how far the node is from the root. Height of a tree. Maximum depth of any node. The height of a tree is the maximum depth among all its nodes. In this case, the height is given as 3. Degree of a node. The number of its children. The degree of a node is the number of children it has. For instance, node A has 3 children, B, C, F, so its degree is 3. Degree of a tree, the maximum number of its node. The degree of a tree is the maximum number of children among all its nodes. It is determined by finding the node with the highest degree. Subtree. Tree consisting of a node and its descendants. A subtree is a tree formed by a node and all its descendants, including the node itself. Edge. Connecting lines of a tree. In a tree, edges are the connecting lines between nodes, representing the relationship and hierarchy in the structure. This slide provides fundamental terms and concepts related to tree structures, helping to understand and describe their properties in relationship with the tree. Number of nodes equals to 9. This indicates that the tree has a total of 9 nodes. Height is equals to 4. The height of the tree is 4, representing the length of the longest path from the root A to a leaf. Root node equals to A. A is identified as the root node, which is the topmost node in the tree and has no parent. Leaves equals to D, H, I, F, and C. The leaves of the tree, also known as external nodes, are D, H, I, F, and C. These are nodes without any children. Interior nodes equals to A, B, E, and G. Interior nodes are nodes within the tree that are not leaves. In this case, A, B, E, and G are interior nodes. Ancestor of H equals to G, E, B, and A. The ancestors of node H are G, E, B, and A. These are nodes on the path from H to the root. Descendants of B equals to D, F, E, G, H, and I. The descendants of node B are D, F, E, G, H, and I. These are nodes below B in hierarchy. Siblings of E equals to F and D. Siblings are nodes that share the same parent. In this case, the siblings of E are F and D. Right subtree of A is equals to C. The right subtree of node A is formed by the subtree rooted at C. This indicates the portion of the tree that descends from the right child of A. Degree of this tree is equals to 3. The degree of the tree is the maximum number of the children among all its nodes. In this instance, the maximum degree is 3. This information collectively provides a detailed overview of the tree, including its size, structure, height, root node, leaves, interior nodes, relationships, and specific characteristics such as the right subtree and degree. Types of tree. General tree. A general tree is a type of tree where no specific constraint or rule is imposed of a hierarchy. In this type of tree, every node may have an unlimited number of children. It is considered a superset of all other types of trees, allowing for a more flexible and arbitrary structure. Binary tree. A binary tree is a specific type of tree in which each parent node can have at most 2 children. These children are typically referred to as the left child and the right child. Binary trees are widely used in various applications, and their structure facilitates efficient searching and sorting operations. Binary search tree, or BST. A binary search tree is a special type of binary tree that imposes specific restrictions on the relationships between nodes. In a BST, the left child of a node must have a value less than or equal to the parent's value, and the right child's value must be greater than or equal to the parent's value. This ordering property enables quick searching and retrieval of elements, making BSTs suitable for applications like sharing and sorting. In summary, general tree allows for an arbitrary number of children per node without specific constraints or hierarchy. Binary tree restricts each parent node to have at most 2 children, simplifying the structure compared to a general tree. Binary search tree, or BST, is a specialized binary tree with an ordering rules, making it efficient for search operation. Binary tree. A binary tree is a tree that adheres to the following properties. Each internal node has at most 2 children, degree of 2. The children are a node or an ordered pair. The children of an internal node are specifically named the left child and the right child. Alternative recursive. Alternative, a binary tree can be defined in a recursive manner. It is either a tree consisting of a single node, or it is a tree whose root has an ordered pair of children, each of which is a binary tree. Applications. Arithmetic expressions. Binary trees are commonly used to represent arithmetic expressions. In such trees, internal nodes represent operators such as additions or multiplications, and the leaves represent operands, numbers or variables. The tree structures reflects the order of operations in the expression. Decision processes. Binary trees can be used to model decision processes. Each internal node represents a decision point, and the left and right children represent the possible outcomes or choices at the decision point. The structure is useful for decision-making algorithms and scenarios. Searching. Binary trees are employed in searching algorithms, particularly in binary search trees. The ordering property of binary search trees facilitates efficient searching and retrieval of elements. This makes binary trees suitable for various searching applications. In summary, a binary tree is a tree structure where each internal node can have at most two children, and the children are ordered as left and right. The recursive definition allows for flexibility in representing binary trees. Applications include modeling arithmetic expressions, decisions processes, and searching algorithms. Binary tree traversal. A tree traversal refers to the specific order in which the nodes of a tree are visited or processed. 3 common tree traversals. In-order traversal. In an in-order traversal, the order of visiting nodes is left, root, right. For each subtree, the left branch is printed before the root, and then the right branch is printed. This traversal is often used for binary search trees to retrieve elements in sorted order. Pre-order traversal. In a pre-order traversal, the order is root, left, and right. The root of each subtree is printed first, followed by the left and right branches. This traversal is used for creating a prefix expression in arithmetic expressions. Pre-order traversal. In a post-order traversal, the order is left, right, and root. The left and right branches of each subtree are printed first, and then the root is printed. This traversal is commonly used in expression trees and for freeing the memory allocated on the nodes. Note on pre and post. The term pre and post in pre-order and post-order refers to when the root is visited during the traversal. In pre-order, the root is visited for the left and right branches. In post-order, the root is visited after the left and right branches. These three traversals are fundamental techniques used in various applications, including expression tree evaluation, sorting and searching algorithms, and more. The choice of traversal depends on the specific requirements of the problem or application. Binary tree traversal examples. In order traversal, left, root, right. Sequence 3, 5, 6, 7, 10, 12, 13, 15, 16, 18, 20, and 23. In the in-order traversal, each subtree's left branch is printed before its root, and then the right branch is printed. The result is a sorted sequence in ascending order, typically for binary search trees. Pre-order traversal, root, left, right. Sequence 15, 5, 3, 12, 10, 6, 7, 13, 16, 20, 18, and 23. In the pre-order traversal, the root of each subtree is printed first, followed by the left and right branches. This sequence can be useful for constructing and prefix expression in arithmetic. Post-order traversal, left, right, and root. Sequence 3, 7, 6, 10, 13, 12, 5, 18, 23, 20, 16, and 15. In the post-order traversal, the left and right branches of each subtree are printed first, and then the root is printed. This sequence is commonly used in expression trees and for freeing memory in tree deletion operations. This sequence represents the order in which the nodes of a binary tree would be visited based on a specific traversal method. Understanding these traversal techniques is crucial for various applications, including tree manipulation, expression evaluation, and tree-based algorithms.